In this video, we're going to take a look at the solutions to this test review. This is a exponential and logarithmic functions test for the advanced functions or MHF4U course. And we have some multiple choice on this page and then some long answer questions on the other pages. So the first multiple choice question, you're given this graph and asked which of these equations would be the one that matches that particular graph. And so you can see it's an exponential shape curve, but it's the one that starts in quadrant 2 fairly steep and then goes asymptotically to the x-axis here. Because it looks like that, the base would have to be a number between 0 and 1, like a half or a third. If you have a graph like 2 to the x, 3 to the x, or 4 to the x, that starts asymptotically close to the x-axis over here, goes through 1, and then gets steep in that direction. So that's how I would know it's not A, B, or E. So let's check and see which one is the right one. And so what you can do is locate a convenient point on the graph. So for example, this point right here is the point -2, 9. So if I put -2 in place of x either here or here, which one gives me the y-coordinate of 9? And so if I take this graph right here, the third, and put the -2 in place of x and evaluate that, notice I have a negative exponent. So a way you can evaluate this without getting into too many reciprocals is if you take the reciprocal of the base, then the exponent changes sign. So a third to the power of -2 is the same as 3 to the power of +2, which equals 9. And so that graph does generate, or that equation does generate the correct y value. If this had been the right one, and we had a half here instead of a third, it would have been a half to the power of -2, and then the base would be 2, 2 squared would be 4, and the point -2, 4 would instead have been the point on the curve. So that's how I know the correct answer is D. For question number 2, a similar kind of question, you're given this one, and it's a logarithmic shape curve, which is the inverse of an exponential curve. And so that's how I would know that A, B, or E cannot be correct. Okay, it's either C or D. It's either the log base 2 of x graph or the log base 5 of x graph. So which one is it? So again, locate a convenient point. That's the point 4, 2. So if we put, see the x coordinate's 4 here. If we put 4 here and evaluate the log base 4 of 2, it actually does equal 2, the y coordinate, because 2 raised to that power of 2 does give you 4. And so that is a point on that graph, and hence C is the correct answer for number 2. For question number 3, you're asked the graph of y equals 7 times 4 to the 2x minus 6 plus 1 has what kind of an asymptote? Vertical, oblique, no asymptote at all, or horizontal. And this is an exponential kind of curve. So very similar to number 1 up here, exponential curves have a horizontal asymptote, whether they look like this or this particular one, the base is 4. So that would be the kind that would go asymptotically down here and then increase very rapidly once you get in quadrant 1 to the right of the y-axis. The +1 actually moves the horizontal asymptote up 1 unit, so it wouldn't be asymptotic to the x-axis, but y equals 1 instead. But that's irrelevant here. It has a horizontal asymptote. That's what you're asked. So A is the correct answer for number 3. For question number 4, we're asked to write each of these, or this one, sorry, in its equivalent logarithmic form. And the base of the power is also the base of the logarithm. So r is the base of this power. So, well, this might be correct, A, but that one can't be because the base is h. So C might be right. That's got a base of r, but D couldn't be because the base is z. And so the way you figure out which one it is, either A or C, is the exponent, the h, would equal the logarithm of z base r, which is answer C. H equals the log of z base r. When I convert from log form to exponential, which is what we're going to do in 5 in a moment, I do it often like this. I start at the base, and that base r raised to that power is equal to this. I kind of do it with arrows. So it would kind of look like this. So r raised to the power of h is equal to the z, which is exactly what that says. So that's why C would be the correct answer for this one. And so in number 5, we use the same idea. Log of a base 8 equals w, then 8 raised to the power of w would equal a. So that's E. 8 raised to the power of w equals a. For number 6, what's the base of this logarithm? If you don't see a base, it's automatically 10. So D is the correct answer for number 6. Flipping over to part 2 and the first question, we're asked to graph this y equals 1.35 to the power of x function and its inverse on the grid. And so I generated a table of values. I used my graphing calculator, but just to show you how we could get any of those. So I started the table at a value of -3 for x. So if you type in 1.35 raised to the power of -3, you get 0.4064, which is where that top number comes from. If we wanted to do the -2, I'll change the exponent to -2, and 0.548, that would round to 7. So that's where that number comes from. Right on down to the last one, I used 10 at the bottom of my table. So if we change this to 10 and evaluate 20.10, that would round to 7. That's where that number comes from. And so that's how you can generate a table of values. And so I plotted all those points. So -3.4 would be that point right there. -2.5, it's a little over half, so that's that point. -1.74 would be that point. 0.1 would be that point, and keep on going. I couldn't plot the last one because it's a little bit too high, the 20.1. But for example, the 8, it's just barely over 11. Would be, we would go to 8 here, and would go up to, that would be 11. So that's that point right there. So you join them with a smooth curve, and that's the graph of y equals 1.35 to the power of x. To graph the inverse, one of the most convenient ways to graph the inverse is just to, if you have a table of values, it's just to switch the x's and y's, because that's what inverse means. This graph's inverse, we switch the x and y, so it would be x equals 1.35 to the power of y. And so all these y's become x's, and all these x's become y's. And if you plot these points, this is the curve that you get. I didn't actually plot them on here, but just to show you, for example, 0.1 was on that curve, so 1.0 is on this curve. So that's the point 1.0 right there. For example, the point, remember I said about the 8.11 point here, the 11.8. So if we go over to 11, up to 8, see, that's that point right there. And so that's what the graph of the inverse would look like. They're actually reflections of each other in that y equals x line. Let me draw that just to demonstrate. So if we draw that line, that's what the y equals x line looks like. And so they would be reflections of each other in that line. Now, the last thing you're asked to do here is write the equation of the inverse in two different ways. So just switching x and y, that's what the exponential form is. The other way is to write it as a log function. And if we convert this to the logarithmic form, like one of those late multiple choice questions, the y would equal the log of x base 1.35. So that's the second way to write the equation for the inverse in a logarithmic form in that case. Flipping down to question number 2, we're asked to evaluate each of the following, showing all steps of reasoning. So the question was, what's the log of 64 base 2? And we can use that power rule. If you can write the 64 as a power of base 2, then, and so 64 actually is 2 to the power 6. If the base of this power and the base of the logarithm are the same, then that just equals the exponent on that power. So that would equal 6. Also, another way to show that this is correct is 2 raised to the power of 6 does equal 64. So that's another reason why that would equal 6. For b here, the log of 81 base 3, and again you can write 81 as a power of 3, it's 3 to the 4th, and so base of the power, base of the logarithm are the same, so it should equal the exponent. So once again, that would equal 4 because 3 raised to the power of 4 does equal 81. For question C here, asked to find the logarithm of this really large number, and it might be convenient to put some commas in here so you can count the zeros more conveniently. So there's 3, 6, 9, 12, 15, and one more makes 16. So that's actually 10 to the power of 16. And again, the base of the power and the base of the logarithm are both 10, so that would equal 16. And again, it equals 16 because 10 raised to the power of 16 equals that large number. What would it be here? Let's see now. Millions, billions, trillions, 10, I think it's quadrillion. I forget what that number is called. But anyway, that's what it would equal, that very large number. For question number 3, you're asked to consider this function and find several things. Domain and range, first of all. Now, it's a logarithmic function, and the vertical asymptote, actually, it says CD here. So let's find the vertical asymptote of that first. So to find the vertical asymptote, you would actually take this 5x minus 10 and set it equal to 0 and solve for x. That gives you where the vertical asymptote is. And so it's a logarithmic shaped curve. There's the vertical asymptote. So actually it would come up, the graphing calculator has limitations. It's not perfect. So it actually does continue to rise here and then kind of flattens out here. So that's where x is 2, and the graph only exists to the right of that. So that's why the domain would be x is greater than 2. It does rise forever up here, and it doesn't actually flatten out completely. It does continue to go down, and so the y values could be any real number whatsoever. To find the x-intercepts, we would set the function equal to 0. So notice I put 0 in place of y here. And so I want to solve to find what x is. So the first thing I'll do is take this term, the whole logarithmic term, over to the left. And so notice the 2/3 changes sign. And so I would next multiply both sides by 3/2 so that this divides out here. And I get rid of the 2/3. So notice I've done that on the right side here. So 7 times 3/2 would be 21/2. Now remember, the denominator 7 is 1, so 1 times 2 is 2 in the denominator here. So the log base 6 of 5x minus 10 would equal that. Now if we put this in its equivalent exponential form, the 5x minus 10 would equal 6 raised to the power of 21/2. And so I'm solving for x, so I'll take the 10 over, there's plus 10, divide out the 5, so that's the exact value for x. If you want to evaluate, that's what it looks like in my graphing calculator. We've got to raise 6 to the power of 21/2, add 10, and then divide by 5. And we get this 29,622,258 to the nearest whole number. That would be the x-intercept, so it's pretty large. Notice how the graph comes. It can take a long time before it gets to the x-axis. It does eventually, but not till you're almost out to 30 million. Where is the function increasing or decreasing? Well, logarithmic functions are either completely increasing or completely decreasing. Because of the negative here, that's why it's the logarithmic function that is decreasing goes down. If that was a positive, actually you would go asymptotically down here and it would rise as you go towards the right. So this is a completely decreasing function, so on the entire domain it's decreasing. And we've already talked about the asymptote for D here, so question number 3 is done. For number 4, we're asked to evaluate the log of 112 base 8 to 4 decimal places. The change of base formula says that this would equal the log of 112 divided by the logarithm of 8. And you can use any base you want. Your calculator does base 10, so that works just fine. And so that gives you about 2.2691, and that's the check. If you evaluate 8 to the power of that 2.2691 number, you should get 112 approximately. This is what it would actually look like in the calculator. Actually, I showed the calculation over here. So we would actually go the log of 112 and divided by the log of 8. Okay, so there's the 2.2691 number. This is only approximate. Notice when I evaluate 8 to the power of that, I got a 111.9957, so it's not exactly 112. If you want to get it to be exactly 112, evaluate 8 raised to the power of my last answer. So that keeps all of the digits, and then you do get exactly 112. Turning over to the next page, in question 5 it says describe the transformations that map y equals log base 3 of x into this function. And the 4 means that there's a vertical stretch of factor 4. The negative means there is a reflection in the x-axis. The x plus 2, the plus 2 means it's translated 2 units to the left. Remember, it's always the opposite sign. And the 6 means that it's translated 6 units up. So those are the transformations for number 5. In question number 6, you're asked what's the equation of the asymptote for this function? And so the asymptote is very much related to the horizontal translation. Logarithmic functions have a vertical asymptote, so it's an x equals asymptote. And so we would set the x minus 3 to 0. You can't take the logarithm of 0, so x minus 3 cannot equal 0. So x equals 3 would be the equation of the vertical asymptote. Now, if you ever happen to have, if you're given the function in that form with the negative 6 multiplied in order to see what the translation horizontally would be, you have to factor that negative 6 out. So we really want it in this form, not in that form. You could still, to find the asymptote, set negative 6x plus 18 equals 0 and solve it, and you still will get 3. That's okay. Flipping over to question number 7. Rewrite each of the following using the power law of logarithms. And so the first one, we're given the log of 4 to the 7th base 3. So this 7 exponent in the power can come down and be multiplied by the 7 in front. So that's equal to 7 times the log of 4 base 3. In question B, you'd have to write the 125 as power. It's 5 cubed, so the 3 can come down in front and write it as 3 times the log of 5 base 8. For question number 8, you're given several equations to solve here. And the first one, 5 equals the log of t base 4. So to solve this for t, you could just turn it back into its equivalent exponential form. 4 raised to the power of 5 would equal to t. And 4 to the 5th is 1024. So that's the root or solution for 8a. For b, in this exponential equation, you can't write 17, well, conveniently as a power of 2. It's not a nice number like 4 or 8 or 32 or something like that. You can write as a power of 2. So we would use logarithms. And so the x in the exponent, okay, when you have a equation with a unknown in the exponent, use a logarithm to solve. So x would equal the log of 17 base 2. And so that's the exact solution. If you want a decimal equivalent to that, take the log of 17 and divide it by the log of 2. And you should get this number right here. This is what it would actually look like in your calculator. We would type in log of 17 and divide it by the log of 2. And so that's where that number comes from. As a check, if you evaluate 2 raised to that power, 4.087. Now, if I want to go get the exact 17, I'll just use the answer that's stored in my calculator and evaluate it, and it gives me exactly 17. If I type in the 4.0875 number, it only gets me close to 17, not exact. But that should be close enough to convince you that you're probably right. For C here, we're given this logarithmic equation. And notice that all the logarithms are the same base. If they're not, then you can't use the rules of logarithms to combine logarithms, etc. So since this is a sum of 2 logarithms, to rewrite this as one single logarithm, it would be logarithm base 3 of x times x minus 1 would equal this logarithm on the right side here. And so to go from this line to this line, since it's log base 3 both sides, we drop the logarithms. Some beginning students who first start working with logarithms think that you're actually like dividing out a log base 3 both sides. That is not what you're doing. Okay, so do not write something like that. This is kind of equivalent to, let's say you had a question like, before we continue here, let's say you had a question like 3 to the power of 2x equals 3 to the 12th. So an exponential equation. Since the bases are both 3, we can drop the bases, kind of like you drop in the logarithms here, and then say, well, since the base is the same, then this exponent on the left must equal this exponent on the right. And that's how I could solve define x. You're not dividing out the bases. You're just dropping the bases and saying, I now know the exponents have to be equal, so I can solve define the exponent, the x. So that's what you're actually doing here. You're dropping the log base 3s. And so x times x minus 1 would equal this 2x over here. And so expand out the x into the x minus 1, get x squared minus x. And I brought the 2x over, so it's minus 2x. If you combine like terms, you get negative 3x. and then we'll factor an x out. So x times x minus 3. So if you set each of these factors to 0, two different factors, so there should be two different answers here. If you set x to 0, you get 0. And when you go x minus 3 equals 0, you get 3 for a solution. Now, in logarithmic equations, always check back into the original equation and make sure that the numbers you got for solutions are going to be valid. So, for example, what I mean by that is this. If we put 0 back in here, even just that first part would be the log of 0 base 3. And you can't take the log of 0. It's not defined. So x is not allowed to be 0. That's actually a restriction for this equation, actually for this expression too. So we drop the 0, and then 3 is the only solution. Now I'm going to do E here next, and then I'll go back and do D and F together, kind of, well, one after another, because they're very similar equations. This was a log equation, so I'll do the E one here next. And so same idea, the log of this plus the log of this, those are both base 4, so we can write as one logarithm by multiplying the x minus 1 and x plus 2. So it's log base 4 of that product would equal to 1. And so the way I would get rid of the logarithm is I could rewrite it in its equivalent exponential form. 4 raised to the power of 1 is equal to the x minus 1 times the x plus 2. So that's, I'm converting from log to exponential form here. And so I'm going to multiply the x minus 1 times x plus 2. X times x is x squared. X times 2 is the 2x. That would be a negative 1x and a minus 2. And 4 to the first is just 4, so 4 on the right. So I brought the 4 over. Negative 2 minus 4 would be negative 6. If I add 2x and negative 1x to get 1x. So that's the equation I have to solve. And it will factor into x plus 3 times x minus 2. The sum number is 1 here. The product's negative 6. 3 and negative 2 do add to 1 and multiply negative 6. So x plus 3 and x minus 2 are the two factors. If we set x plus 3 to 0, we get negative 3. And then x minus 2 to 0, we get positive 2. Now x can't be negative 3. Because if I put negative 3 in place of x here, then that's going to be a negative 4 that I'm taking the log of. And so that's not defined. So x could be 2. If you put 2 in here, that's positive, and 2 in there, that's positive, and that's okay. So the only solution here would be 2. On to question D. We're given this equation, and this is kind of like, there's exponential parts to this. But this is really like a quadratic type equation, and this really isn't much different than if somebody asked you to solve this by factoring. If you're going to factor that, you want to find two numbers that add to 2, multiply negative 15, which would be 5 and negative 3, and so we would write x plus 5 and x minus 3. And I could set each of those to 0 and solve for x. Now, same idea here. The 3 to the 2x, that's kind of like the quadratic term. It's got an exponential part to it, but that's the same idea as the x squared. The 2 times 3x, so this is actually like the linear term, like the 2x here. So if you thought of the 3x as the x, or whatever variable you want to use, we shouldn't really say 3x equals x. And this is the quadratic term, and this is like factoring a quadratic. To factor this, these two factors would have to start with a 3 to the x, because 3 to the x times another 3 to the x is 3 to the 2x. Remember, you add the exponents, 1x and 1x is 2x, just like x times x is x squared. Same idea, you add the exponents. So that's why each of these factors would have to start with a 3 to the power of x. And you need to find two numbers to add to 2, multiply negative 15, which is the same 5 and negative 3 over here. So that's plus 5 and a minus 3. Just to check that this does expand out to give you this, 3 to the x times 3 to the x would be 3 to the 2x. And then if you multiply, well, actually, let's do this one next. That would be a minus 3 times 3 to the x. Now, it is possible to combine those together, if you're noticing that, but I'm not going to do that. If you multiply these together, that would be a plus a 5 times 3 to the x. And I'm kind of running out of room, but 5 times negative 3 is negative 15 on the end. So there's the negative 15 on the end, the 3 to the 2x here, and if you add negative 3 times 3 to the x and 5 times 3 to the x, you get 2 times, like terms, you get 2 times 3 to the x. So that just demonstrates that that factoring is correct. Now you set each factor to 0, so 3 to the x plus 5 equals 0, and 3 to the x minus 3 equals 0. When you bring the 5 over, you get 3 to the x equals negative 5, which has no solution because you cannot raise any positive base to any exponent and get a negative. So there's no solution from that factor there. But this one there is. If we set 3 to the x minus 3 to 0 and bring over to 3, you get 3 to the x equals, well, 3. And there's actually an exponent of 1 here. And so x would have to equal 1. So 1 is the solution to D, only 1. Similar idea in F, but we have the 10 on the right side here. So the 15 wasn't, it was already everything on one side over here. So you should bring the 10 over first, and so it'll be minus 10 on the left. And so in order to factor this, we need to find two numbers to add to 3 and multiply negative 10, which would be 5 and negative 2. And so since this is a 7 to the power of 2x, each factor has to start with a 7 to the power of 1x. So 7 to the x times 7 to the x is 7 to the 2x. And so the numbers again were 5 and negative 2 that add to 3 and multiply negative 10. So plus 5 minus 2 at the end of each of these factors. Set each of these to 0, and we do that for this one here. We get, well, very similar to the 3x. In this case, it's 7 to the x equals negative 5. Would have no solution. The second one here, when you bring the 2 over, the negative 2 becomes positive. So you have 7 to the x equals 2. And so to solve for x, I can't write 2 as a power of 7. X would equal the log of 2 base 7. So that's the exact solution to this equation. If you want a decimal equivalent, take the log of 2 and divide it by the log of 7. Looks just like this. Log 2 divided by the log of 7. And that's where the 0.3562 comes from. Flipping over to the next page. For question number 9, you're told that the difference between sound levels and decibels can be found using this equation. So the one sound decibel reading minus the second round decibel reading is equal to 10 times the log of the ratio of their intensities. Ratio of intensities is in watts per square meter. The betas are in decibels. So we're asked in A, it says how many times more intense is pain threshold, which is 130 decibels approximately, than a jackhammer at 100 decibels. Well, so we take our formula, and so 130 and 100 are the two decibel readings, so we subtract those. And when it says how many times more intense, we're looking for this ratio. That's what we're asked to find, the ratio of the intensities. So we want to solve for I2 over I1. So 130 minus 100 is 30. If we divide out the 10 here, that's why there's no number here. 30 divided by 10 is 3. Remember, the base of the logarithm, if you don't see a base, is 10. So 10 raised to the power of 3 would equal this ratio. So I1 over I2 equals 10 cubed, which is 1,000. So the pain threshold is 1,000 times more intense a sound than a jackhammer. In question B, we're told that the sound intensity produced by a military jet at 20 meters away in watts per square meter is 1 times 10 squared, so it would be 100 watts per square meter. That's a pretty intense sound, which is 140 decibels. So as I actually pass the pain threshold. Another sound has an intensity of 10 to the minus 8 watts per square meter. What would be the decibel reading for this second or lower sound? So again, here's our formula. We're looking for one of the betas. So I'm going to let beta 2 be the 140. I could let beta 2 be the unknown and beta 1 be the other one. So it just depends on which way you want to rate the ratio. It's simpler to rate it this way. I know that beta 1 is actually a lower sound, so it'll have a lower decibel reading. We don't want to get into negatives here. That would just complicate things a bit. So that's why I let beta 1 be the unknown we're trying to find. The military jet has an intensity of 1 times 10 to the power 2 watts per square meter. And the second sound is 1 times 10 to the 8th, negative 8 watts per square meter. And so if you divide these And actually, because these are in scientific notation, these are both ones, it's really just 10 squared divided by 10 to the power of negative 8. Actually, I don't need that bracket, I guess, do I? So you get 1 times 10 to the 10th, or it's 10 to the power of 10. You can actually use the exponent rules and say, well, it's 2 take away negative 8, which is, again, 10 to the 10th. So that's what that simplifies to. Since the base of this logarithm is 10, 10 raised, log base 10 of 10 to the 10th, the base of the power and the base of the logarithm are the same, so it would actually equal the exponent. You could actually type that in your calculator, but that would just equal that exponent 10. So basically we just have 10 times 10 on the right here, which is 100. So 140 minus beta 1 is 100. So that sound, I just dropped the subscript, I call it beta, would be 140 minus 100. So it had to be 40 decibels. 140 minus 40 gives you 100. So the second sound has a decibel reading of 140. Sorry, of 40. Last question here. This is an earthquake one using the Richter scale. The magnitude of M of an earthquake is measured using the Richter scale, and which is M equals the log of their intensity, similar to the one above. I is the intensity of the earthquake you're talking about, and the I sub 0 or I naught is the intensity of a standard low-level one. So you're asked, how much more intense is an 8.5 magnitude earthquake than a 1.7 magnitude one? So we use our formula, and similar to the one in the sound one in question 9, M is, in this case, we're going to use the difference between the two magnitudes. So we would take 8.5 and subtract 1.7. So the difference between them is a Richter scale reading of 6.8, because that's what M is. It's a Richter scale reading. So in this case, it's the difference between the two. So it would equal the log of I over I naught, the ratio that we're looking for. And so in order to solve for I over I naught, the base of the logarithm is 10, so 10 raised to the power 6.8 gives you this number here, so a little over 6.3 million. So an 8.5 magnitude earthquake is about 6.3 million times more intense than a 1.7 magnitude quake. So considerable difference in their intensities. And that's the end of the video.